the Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program explores the basics of forging. Forging is the controlled deformation of metal into specific shapes by the use of compressive forces. These forces are applied through tools and dies, driven mainly by hammers, which deform the workpiece by high-velocity impact, or presses, which deform the workpiece through controlled high pressures. Forging is one of the oldest metalworking processes, dating as far back as 8000 BC. It is utilized today to reduce the cross-section, improve the metallurgical microstructure, provide directional grain flow, and eliminate porosity of cast ingot in fabricating wrought mill forms, and to form discrete parts to near net shape from these wrought mill forms, further refining microstructure and directional grain flow. Because of these effects on microstructure and grain flow, the mechanical performance of wrought mill forms and parts is typically superior to that of cast metals. All metals and alloys are forgeable. The extent to which they can be forged or deformed without fracture is called forgeability. Forgeability is a qualitative rating expressed in terms such as excellent or high, good, fair, and poor or low. Forgeability depends on the metal's or alloy's composition, crystal structure, and mechanical properties, and pertains to a specific temperature range. The greater this temperature range, the better, since narrow ranges are more difficult to maintain during the process. Since heat increases forgeability, most forging is done on heated workpieces. However, forging can be performed at room temperature, which is called cold forging. Aluminum alloys, copper alloys, and magnesium alloys rank high in forgeability, followed by plain carbon steels, low and high alloy steels, nickel alloys, and titanium alloys. Some superalloys, especially certain nickel-based types, are more difficult to forge. Refractory metals have good to fair forgeability, depending on the metal or alloy. Beryllium is the least forgeable metal. Hot forging temperatures range from as low as 93 degrees Celsius for aluminum alloys to as high as 1650 degrees Celsius for refractory metal alloys. There are two primary types of forging: open die forging and impression die forging. But there are also other related forging processes. Open die forging is performed on ingot, billet, bar, or a preform, and is the deformation of a workpiece between flat or shaped dies without completely restricting metal flow. This deformation can result in lengthening of the workpiece while reducing its cross-section, upsetting regions along the length to greater sizes than adjacent regions, or bulging the workpiece's cross-section while reducing its length. Lengthening and upsetting are typically done using multiple impacts, as the workpiece is incrementally advanced lengthwise and rotated about its longitudinal axis. There is essentially no limit to the size of forgings that can be made using open die forging. They can range from a few centimeters to 30 meters in length and weigh from a few to up to several 100,000 kilograms. Although fairly complex shapes can be made using open die forging, most are rather simple solids or hollows requiring considerable machining to achieve final shape. Forgings are produced using simple flat, V-shaped, or semi-round dies. Various accessory tools are also used, including saddles, blocks, rings, mandrels, and punches. To withstand forging temperatures, abrasion, and impact, dies and accessory tools are usually made of hot work tool steels or medium carbon alloy steels. Lubricants are not always used in open die forging. When they are required, these lubricants are usually graphite dispersed in oil or water. Handling equipment is used for various purposes in open die forging, such as workpiece transfer from heating furnace to forging machine, manipulation during forging, and offloading of finished forgings. This handling equipment includes manually handled tongs, floor vehicles with heavy-duty tongs, cranes with lifting devices, and rotators to rotate the workpiece about its central axis. With manipulators, the sequence of forging operations can be controlled by the machine operator or programmed for automatic operation. Common applications for the open die forgings include multi-diameter or eccentric shafts, as well as rings, spindles, gears, wheels, tools and dies, and many other parts. Impression die forging, also called closed die forging, is the deformation of metal at forging temperature within one or more die impressions or cavities. It is performed both in presses and hammers. Workpieces may be round or rectangular in cross-section or flat discs, and the dies are sometimes integrally heated to minimize chilling and cooling of the workpiece. For simple shapes, impression die forging can be performed in a single press stroke. More often, however, several strokes of different force are used with dies having several impressions for sequential preforming and finish forging operations. Preforming operations may include edging to increase the workpiece cross-section, blocking to refine the shape for finish forging, and finish forging to complete the shape. In finish forging, the bulk of the metal is forced into the impression, while a thin layer, called flash, flows out between the dies at the parting plane, surrounding the forging. Flash comprises a flat region called the land, and sometimes a bulbous region at the end of the land created by a gutter in the upper die. The thin flash cools rapidly, increasing pressure within the impression, which assists metal flow in the impression details. Once finish forging is complete, the flash is removed either manually or with trimming dies. Flashless impression die forgings also can be made, reducing metal consumption. However, the size and shape of the workpiece must be more accurately controlled to ensure that all the metal flows into the impression. Impression die forging requires accurate control of workpiece temperature, die alignment, and workpiece volume to ensure filling all part details in the impression without generating excessive pressure on the equipment. Lubricants, most often graphite in oil or water, are commonly used for impression die forging. Lubricants minimize friction, abrasion, and heat loss. They enhance metal flow and permit release of the forging from the dies. Impression die forging is typically used to produce more complex shapes than open die forging, and the forgings are more precise and much closer to net shape, often reducing the need for subsequent machining. Complexity of shape that can be forged depends on the forgeability of the workpiece metal or alloy. Long, thin ribs and webs are difficult to impart because of the large volume of metal that has to flow in a confined region. Die cost for impression die forging is greater than for open die forging so the process is usually limited to high-quantity production. However, reduced machining may offset higher die cost, even for limited production. Also, the metallurgical structure induced by impression die forging may be mandatory for required part performance. Automobile engine connecting rods exemplify parts required in high quantities. Aircraft bulkheads and aircraft engine parts are made in much fewer quantities, yet are economically justified. Although very large parts, measured in thousands of kilograms, have been made, most impression die forgings are small to moderate in size. Open die and impression die forging encompass a wide variety of specific processes, which include seamless ring rolling, hot die forging, and isothermal forging. Seamless ring rolling is the circumferential expansion and cross-section reduction of a centrally pierced disc-shaped workpiece on a ring rolling machine. A variety of cross-sectional profiles can be produced, such as square, rectangular, and sections with interior and exterior contours. The workpiece is placed between an undriven roll or mandrel and a driven outer roll. The outer roll rotates the workpiece, which by friction rotates the mandrel. As the gap between the driven roll and mandrel decreases, the workpiece cross-section thins and the ring diameter expands. The cross-section profile is controlled by the shape of the mandrel and the driven roll. Cross-section height is controlled by the driven roll or by a conical axial roll or rolls on the opposite side. Most ring-rolled forgings range from 20 centimeters to over 1 meter in diameter, with cross-sections between 5 to 20 centimeters high and 1 to 5 centimeters thick. However, much larger and smaller ones can be produced. Ring roll forging is used to produce gear blanks, bearing races, valve bodies, wheels, turbine components, and many other parts. Hot die forging and isothermal forging both refer to the use of heated dies in forging a workpiece that is heated to its forging temperature range. The distinction between hot die forging and isothermal forging is a matter of die temperature. In conventional hot die forging, the dies are maintained at a temperature less than that of the workpiece's forging temperature range. In isothermal forging, they are maintained at the workpiece's forging temperature range. Use of heated dies is important in forging conductive metals, such as aluminum and high copper alloys, as well as alloys having a narrow forging temperature range, such as certain titanium alloys and nickel superalloys. Using heated dies reduces or eliminates chilling of the workpiece. This allows forging more complex shapes, forging closer to net shape, and forging to greater precision than in conventional forging. Parts forged to greater precision than by conventional forging are called precision forgings. For aluminum alloys and titanium alloys, precision forging can reduce draft or taper of sidewalls and internal projections. Rib and web features can also be thinner. In addition, precision forging can generate a smooth surface finish. The computer has had a marked effect in enhancing forging technology. With computer programs, dies can be designed more efficiently for specific parts or families of parts and drawings generated on demand. Optimum forging sequences based on part geometry also can be established and forging requirements determined for press selection. Computer-controlled forging systems can provide virtually full automation. They can markedly increase production rates, reduce rejects, conserve metal, and reduce labor costs. Automated operations can include billet or bar loading, furnace heating, hot shearing to workpiece length, preforming, lubrication, single or multiple die forging operations, trimming, straightening, unloading the forging, and die changing. Let's review the material contained in this videotape. Forging is the controlled deformation of metal into specific shapes by compressive forces applied through tools and dies driven by hammers and presses. All metals and alloys are forgeable. Forgeability, the extent to which they can be deformed, depends on their composition, crystal structure, and mechanical properties. Forging reduces the cross-section, improves the metallurgical microstructure, provides directional grain flow, and eliminates porosity of cast ingot. In forging parts from wrought mill forms, forging can further refine microstructure and grain flow. The two principal types of forging are open die forging and impression die forging. Open die forging is deformation of the workpiece between flat or shaped dies without completely restricting metal flow. Open die forging is used in the production of wrought mill forms and to produce parts of simple shape. Impression die forging, also called closed die forging, is the deformation of metal within one or more die impressions or cavities. It is used to form parts which can be quite complex in shape. Open die and impression die forging encompass many specific processes, including seamless ring rolling, hot die forging, and isothermal forging. Seamless ring rolling is the circumferential expansion and cross-section reduction of a centrally pierced disc-shaped workpiece. It is used to make gear blanks, wheels, and many other parts. Hot die forging and isothermal forging refer to the use of integrally heated dies in forging a workpiece heated to its forging temperature range. In most hot forging, dies are maintained at a lower temperature than the workpiece. In isothermal forging, the dies are kept at the forging temperature range of the workpiece. The computer has had a marked effect in enhancing forging technology, from die design and analysis to virtually full computer-controlled forging automation.